All right, okay. My project was about building a model to classify X-ray images is either pneumonia or normal. So basically, this is the criteria I'm going to use here. We have motivation. I'm going to start by talking about what motivated me to do this particular project. Then I'm going to talk about the methodology, that is the methods that I used and how I came about those methods. And finally, I'll talk about my results and conclusions. So we are all aware of COVID-19 and it's being declared as a global pandemic by the World Health Organization. Just recently, I think somewhere in the month of February, it was declared as a global pandemic. And as soon as that happened, many researchers just have jumped in to help provide a solution to this global pandemic. And one of the best ways to provide a solution in terms of diagnosis is machine learning. So, but machine learning, there are different types of machine learning. But what I focus on in this research is deep learning using convolutional neural network. Because what I'm classifying is whether an image has COVID or not. But you would come to understand from this presentation that the samples data set that I got only had very little classification of what it means for an X-ray lung image to be covered or not. As a matter of fact, the classifications and the labels are with respect to either it's a normal lung image or it's a pneumonia. But if it's a pneumonia, we do not know whether it's COVID as a result of a bacteria or as a result of a virus, other virus other than COVID-19. All right, so I chose deep learning neural network because neural networks are good at handling image data, building features and classifications, feature maps out of the images that you have. So over here is a sample image that you want to classify if it's COVID or not, but in this case, whether it's a pneumonia or not. And what are we going to use? We are going to be using binary classification to do that. Okay, so let's look at the methodology. Starting with data acquisition and description. So basically, the data was obtained from Kaggle. This website is where I got the data from. And in Python, I tried to show what the data looks like. This is actually a CSV file that comes with the data that tells you how the files are organized in the folders. So you have your X-ray image name, you have your label, and you have your data set type. So data set type is either train or test, and the label is either normal or pneumonia. So basically, the binary classification is going to classify an image as normal or an image as being pneumonia. What I did was to assign a label of 0 to normal and 1 to pneumonia. So this function here helps me to load the image from the folders. And before that is done, you would realize that the image, first of all, has to be reduced, resized. Once the image is loaded, it has to be resized. And I resized 224 by 224 pixels. And then save them as NumPy array for further processing using this statement over here. One will realize that this if conditional loop, what I did actually was to build some sort of a dictionary using the CSV file that was provided with the data. And at the end, I'll put a link there for you to check it out. So basically, image name is the um, is a list of image names which was gotten from the CSV file. So I want to check if the file name that I get from the path supplied is contained in the image names. If it's contained in the image names, then what I can do is to check in the dictionary that I saved. So dictionary is a dictionary of image names as keys and either 0 or 1 as the values representing normal or I mean this is how it's coded in normal. So, and that tells you that this will build your X data and your Y data. And I named it data because I'm going to pass the path of the test image and the path of the training image here so that it's a generic name representing that training test. Okay, so the model architecture. So I experimented with different types of models and some really had high parameters. So it's very difficult for the model to be trained using like a batch size, which was like 32. So this is the representation of the model. This one was printed from Python using graphics. So the model actually has 5 convolutional layers: 1, 2, 3, 4, and then 5. And each convolutional layers have about almost a maximum of 128 units. That is like filters that was used. So it's a 3 by 3 filter with just one stripe, and a max pooling, a 2 by 2 max pooling, and dropout layers, which are used to prevent overfitting. And these convolution layers are used to extract the features of the units. And then I have 2 dense layers. Last dense layer has 2 units, and then an activation of softmax because I'm going to do a binary classification. So my final output is the representative of what I expect. 0 or 1. All right, so we move on to the results. So now what we see here is the model accuracy and with respect to epoch, which is the number of cycles. Let's say. So in this model, I actually set the epoch to be 100 and then set um, early stopping, with 30, a patience of 30, meaning that it should, if I have the same accuracy, validation accuracy, like 30 times, it should stop the prediction, stop the fitting of the model, and give me the highest accuracy that was obtained. So at an epoch of about 64, I had an accuracy of 92, which was, I believe, is good. But the results after testing was like. So what I use to compile my model is binary, the Adam optimizer, and a loss function using the binary processor. As you can see, it's very high accuracy. So this is how I finally tested my model. So I have my image, I load my image, convert it to LA, which is like 2-dimensional. That's what I use because that was the image was 2-dimensional. So I'm just converting to a 2-dimensional image. And so I chose 2 images. One is a normal image, which is IM002. So I expect this to tell me that I expect the model to predict that it's a normal image, and that is what I got. So the first term here shows that it's a normal image. 100%. 1.0, 100%. Second term is not 0% like normal. And second makes the pneumonia image, which the model accurately predicted to be 100%. So I think I got very good results for this. So in all, what I can say is this sequential convolution neural network did what it was supposed to do with an accuracy of 92.8 and was able to predict really well. But there were just a few challenges here. So I believe have higher accuracies with larger data sets and better pre-processing. Because over here, I didn't do much of pre-processing except to resize the images and to compare them to early form. So with the larger data sets, models should be better. And also, in order to make, since this is solving a problem, in order to make it beneficial to clinicians, we could just build an online platform where it's easy for doctors and